Hello guys, welcome to the fourth lesson where we'll be looking at Newton's laws of motion. Now, we have run through lesson 1 up to 3, which basically serves as a foundation, right, for us to be able to understand the laws of motion. Now we are at the core of this topic where we're now going to look at the actual laws and see how we can apply them in solving problems. Right, we are getting closer and closer to now being able to tackle question papers. Right, I believe that as you went through those lessons, they were able to come as a revision to you and maybe rectify some of the concepts that they may have been confusing to you. Right, so let's begin with lesson 4. Right. The lesson 4 is solely focused on Newton's first law of motion. Right. The first law of motion states that in the absence of a net force, every object will remain stationary or will remain in motion with a constant velocity along a straight line. Now, let's break this law and see what it means, right? Stationary, I'm sure you already know, a lot of you, that it means rest, something that is not moving, right? And also when we say something has a constant velocity, it means that so velocity would mean that it's moving, but the velocity does not change. Constant would mean it does not change. It's the same throughout, right? So the symbol for the Newton's first law is sometimes written as N1, right? So we'll use that just so we were able to speak about it easily and quickly without writing that long statement that says Newton's first law of motion. We'll just call it N1. Now, what do we learn from Newton's first law? What are the conclusions that can we take from this law? Right. The first conclusion is that if there is no net force, the object is not moving. So I want you to imagine a situation where we have a horizontal surface, and on this horizontal surface we have a box like that that's sitting on the surface. Now with this box, there are no any forces applied on the box, right? It's just sitting there on the horizontal surface. Now, because there are no forces, it means that the net force is going to be 0 newtons, right? And that means the object will not move. It does not have velocity. The velocity is 0 meters per second, right? This means that, so Newton's first law says that this object will remain being in this type of motion. It will remain being in this motion, right? It will not change its motion, right? Because there is no net force. Right? The second point that Newton's second law speaks about, so that was the first part here, to say that if there is no net force, the object is not moving. It will remain that at that point. The other one is that sometimes there is no net force, but the object is actually moving with a constant velocity. For this one, I want you to imagine throwing a ball horizontally to the right. Let's say we have a ball like this, and then we throw it horizontally to the right, so that this ball moves horizontally with a velocity v, right? It will have some velocity v there. It could be any number, 2 meters per second, any number. But now this velocity becomes constant. What does that mean? That means when the ball gets to this point somewhere here, right, you'll find that the velocity hasn't changed. It still has the same velocity v. Even when it gets to this point here, as it moves horizontally, you will come to learn that this ball still has the same velocity v. It does not change velocity as it moves on a straight line, on a horizontal straight line, right? So this will be true if there is no net force. If there is no net force, if the net force is equal to 0 newton, right? But now notice the difference between these two scenarios. Here and this one here. The difference is that the net force is 0 and here the velocity is 0. But now on this one we do have a velocity, let's say 2 meters per second, but it does not change. It continues being 2 meters per second as that object moves along a straight line, along the horizontal, right? So that's what this law says. If there's no net force, we see these two behaviors, we see these two types of motion where an object just stays where it is or it moves along a horizontal line without changing its velocity. Right. Now, from this law, we can see that, because this happens when there is an absence of net force. If there is no net force, already we can also conclude from this law that if there is a net force, if a net force happens to be available, if there is a net force, it will then cause a change in motion of the object. So what are we saying? We're saying that if on this scenario here, on this diagram, I start applying some form of a force here, I need to use a pen instead. If I apply some form of a force here, F, right, the surfaces also will produce some form of friction here. Let's say the object moves so that we have kinetic friction here, right? Then we then have a net force. The net force will not be 0 in this case. When you do your net force, remember you can also choose direction such that anything that goes in the x to the right is positive and anything in that direction is also positive. Now here we'll have force, the applied force, this one here because it goes to the right, and minus the frictional force because it's going the negative direction. When you add here, it will be positive minus, which gives you a minus. Then you have the kinetic friction force. Now remember, this comes from the definition of the net force in lesson 1. That's why I said lesson 1, 2, and 3, they are a foundation in helping us to understand these laws. So what I've used here was the definition of the net force, where we said the net force is the vector sum of all forces acting on an object. It gives us the overall effect of these individual forces acting on the object. So now, once we have this net force, it's not 0 anymore. We then have a change in motion. This object will suddenly not have a 0 velocity. It will start having some form of velocity here. Let's say we will have v is equals to some number there, 2 meters per second. It will start moving. The motion will change. There will be change in motion. The same scenario is true. Remember here we said we are throwing a ball horizontally and there are no forces here acting on this ball, so it will continue moving in that horizontal line with a constant velocity. If somehow we introduce, let's say in this scenario, the force of gravity, right, then suddenly we'll have a net force, because remember the force of gravity will be acting vertically downwards like that, Fg, right? We talked about the force of gravity in lesson 3, right? Again, those lessons, they come as a foundation in assisting us to understand the laws, right? So now if there is a force of gravity, you will see that the ball will start changing its path. It will move like this. It will start coming down here. I just want to use this color here. It will start coming down here because there is some force here. There is a force of gravity that changes its path. It then changes its motion. As we said here, that the motion will change if there is some form of a net force, because this force of gravity will introduce a net force, will make this net force not to be 0, right? Another way of looking at this really is, maybe let me use an eraser here. Another way of looking at this situation really is, let's say we put a wall here. Let's say the ball hits a wall instead of introducing gravity, right? Let's say the ball hits a wall here. So let's say we have, let me change my pen. Let's say we have a wall and the ball comes in contact with the wall. The wall will exert a force that goes in this direction, right? So this will cause some form of a net force, because now when you come here, it won't be 0 anymore. You'll have to incorporate here when you add your forces this F here. Now this force will cause the object to change and move in the opposite direction, to go in this direction, right? To go in this direction. So there is a change in motion when there is a net force. Right. This statement actually prepares us to look at Newton's second law in our next lesson. Right. I hope this is clear and straightforward. That's what Newton's law, first law of motion, is all about. There's two conditions. The object will remain stationary if there are no forces acting on it, or it will continue moving with a constant velocity, right, or speed along a straight line if there is no net force. But when we have a net force, the motion evidently changes, right? Another concept that I like us to have a look at is what we call inertia, right? Inertia is defined as the natural tendency, right, or property of an object to resist any attempt to changes in its motion. Right, I think you know this inertia. You have observed this phenomenon. Say for example, you have, you know, let's say a box on a horizontal surface. Let's say you have a box on a horizontal surface, and you try to push this box with a force F. What naturally happens, or so the box was stationary sitting on a horizontal surface. What naturally happens is that the box wouldn't just move immediately. It will sort of resist, right? It will sort of try to oppose your motion. It won't move immediately, you know. That property, we call it inertia, right? That property, we call it inertia. Objects do not like to just move without offering some form of resistance. Another interesting one that we can have a look is when we are having, let's say, we're having a bus, right? Let's say we are having a bus here, and you are standing on the bus here. You're inside the bus and you are standing in here, and let's say the bus is moving with some velocity v here, right? 120 kilometers per hour, let's say, for instance. And suddenly then the driver hits the brakes, right? And the bus stops, right? Suddenly, what will happen with your body? Remember, when the bus is moving with the velocity of 120 here kilometers per hour, right? This means that you are also moving with that velocity because you are inside the bus. You are moving with the velocity that is the same. You are moving with the velocity that is the same as that one of the bus because you're inside the bus. Now, when the driver hits the brakes, your body would want to continue going forward with that velocity. It will resist stopping as the bus stops. It will want to go forward with that velocity. This is the reason why when the bus stops, you know your body will sort of move forward. That property, we call it inertia, right? So objects tend to have that resistance. It doesn't want to change that motion of moving at this speed of 120 kilometers per hour. So that's what we call inertia, is the natural tendency of an object to resist any attempt to change its motion. Right, now I think if you're listening to me very carefully, how we stated Newton's first law and how we defining inertia, you can see a lot of similarities, because we are saying here that in the first scenario here, we are saying that an object is stationary, right? It remains stationary. Then we start putting in some force to create the net force. So the net force was 0 when it was stationary. Then we're creating some net force there. By doing so, we then change the motion of that object. I mean, that's the first condition of Newton's first law, where we're saying if there is no net force, the object is not moving. It will only move when you put a net force, right? So this is similar to the first part of Newton's first law. Now here we're having a bus that's moving with a velocity of 120 kilometers per hour. We can assume that it's constant, it's not changing, right? And you are also moving at that velocity. But when we suddenly hit the brakes, remember when we hit the brakes, the brake will exert a force that goes in this direction to stop the motion of the bus that the bus is moving with to the forward direction, as I'm drawing this arrow here, right? But now when that happens, your body wants to remain in this motion of moving at a constant speed of 120 kilometers per hour of that bus, right? That is similar to the second condition of Newton's second law, where we say, look, if there is no net force, because when we are moving here with a constant velocity of 120, right, there is no net force. The net force comes when we're hitting the brakes, right? It goes in that direction, stopping the bus. Then the body, that's when now changes its motion, and it actually resists before it can even move forward, as we said, because of that inertia. Now, so inertia has in it those two statements of Newton's first law. For that reason, oftentimes than not, Newton's first law is called the law of inertia, because inertia allows objects to resist changes in their motion. They want to remain stationary, or they want to move with a constant speed, right, until there's a net force that changes their motion. So there's a difference between defining inertia, where you'll be just defining it to say, is this tendency to not allow changing your motion. But the law of inertia is the fact that you want to remain the way you were until there's a net force. So we call inertia the law of inertia. We call Newton's first law, I mean to say, the law of inertia. So these are the same thing. So if you get to an exam paper and they say state the law of inertia, what they want you to do is really state Newton's first law of motion. They want you to state Newton's first law of motion, right? Another interesting concept that we study here, and in the previous lesson 3, we touched on it a little bit, and I said I will define it properly here. And I said that because in physics we define mass completely different compared to how we actually define it in chemistry, right? So in physics we say inertia is the measure of mass is the measure of an object's inertia. What do I mean? What I mean is that if you have, let's say, these two scenarios here, maybe I could erase instead of redrawing. Let's say you have these two scenarios here. You have a bus, right? That's stationary, right? It's stationary on a horizontal surface. It's stationary on a horizontal surface. You also have a box here. You also have a box on a horizontal surface. It's also stationary. Both these two objects are stationary, right? If we want to understand the concept mass, right, we're saying it's a measure of inertia. If I try to move this box, you will find that I will exert a force, right? This box will give me some form of resistance because it has inertia, but you'll find that it's a lot easier to move it, even if it can resist a little bit, but it's a lot easier to move it compared to when I push the bus. If I push the bus, it will be much more difficult to actually move it. And in fact, if I'm alone, I'll probably not be able to move that bus because it's difficult. The inertia here is big. So what I'm saying here is that I'm saying the inertia here, the resistance here on the box is small. It's smaller, and here it's much bigger, right? The resistance, remember, inertia is the resistance to change motion, right? So the resistance here, the inertia, let me do this, the inertia, right, when you compare between these two objects, the inertia here is much smaller compared to here, right? This tells you that this object, right, has a small inertia because it's small in size, right? And this one has a bigger inertia because it's much bigger in size, right? That's what we call mass, is a measure of inertia. We're measuring how difficult or how easy it is to move an object. How difficult is it for an object to resist changes in its motion? That's how we define inertia in physics. I mean, physics it's concerned with motion, so that's how we define inertia we define mass, I mean, in terms of how it moves, how it behaves when you try to move it. So is the measure, when we say the measure, we're measuring how difficult it is to move an object or how easy it is. So objects that are easy to move or even to stop, right, they must have a small mass than those that are difficult to start moving or to stop, because they'll be big in terms of you having to stop them, right? They'll have a bigger mass, right? So The symbol for mass is normally M. So, you'll find that usually when they give you problems, they will, be writing this as M or this as M. Sometimes we'll say mass of the box. So here they will say M of the box, and then here we'll say M of the bus. We'll write the subscript there to distinguish between the two. That's how we'll use the symbol. And already we talked about this to say the mass is measured in kilograms, right? The mass is measured in kilograms. Right? That's the SI unit that we use in our calculations. Yes, sometimes you can be given mass in grams. You can be given mass in grams. That means you have to convert this to kilograms. Right? You have to convert this to kilograms. We use this in calculations and reporting our answers. Right. One thing also that's very interesting here is that mass is a scalar quantity. Right. In our previous lessons, when we introduced, I think it was lesson 1, when we introduced a force, we defined a vector quantity. So now here, that's where we're gonna define properly what a scalar quantity is. Actually, a scalar quantity is a concept that goes hand in hand with a vector quantity. So this would be a physical quantity that only has the magnitude but no direction, right? No direction. Is a physical quantity that only has the magnitude but no direction. Remember, we said magnitude is size, so it's a number with the SI unit. So if I say the bus has a mass of, so let me quickly move the highlighter. If we say the mass of the bus is 1000 kilogram, right? The 1000 and the kilogram here is the size, is what we call the magnitude. So the size is seen by reporting it or recording it as a number and the SI unit, right? And in this case, you'd see that with a mass, I cannot say it's 1000 kilogram to the right. It wouldn't make sense, right? How can you say to the right? Because mass actually measures the resistance, the inertia of this bus, how easy it is to move the bus or how difficult it is to measure. Is the bus big or small? That's what we're interested in. We're only interested in the magnitude, the size of this quantity. Such quantities are called scalar quantities, and mass is one such quantity, is a scalar quantity. Grade 11s and 12s, thank you for being with me on this lesson. This is not really a long lesson, it's a very simple lesson, and I hope it made sense, right? We'll move on to the second law and the third law in lesson 5 and 6. Then we'll be able to then now start doing calculation problems, right? And at the end, I think some of you, if already you have went to the link and downloaded the study guides, you should have seen that at the end I've compiled questions, exam-like questions that start with the multiple choice questions and do long questions where we look at different scenarios, different possible questions that you may get in an exam. So we are paving our way towards that, where we'll now practice how to solve those problems. Please stay tuned for the next lesson 5, where we'll be looking at Newton's second law. May the force be with you.